So suppose we have y equal f of x. And we approximate, let's say, x right there. That's f of x. And if we move to x plus delta x, so we move a small delta x, the change in y would be right there, that difference. So if I have to extend the line, that would be the change in y. If I draw a tangent line right there, dy will be this difference. So you'll notice there's a small margin of error right there. You're off slightly if you use the tangent line instead of using the actual. Now the actual is a lot of work. The approximate gives you a very good idea of how this works. And this is how we find it. Given y equal f of x, we take a derivative, and if we cross multiply, we say the actual change is roughly the approximate. So approximate change in y is the rate of change, which is the derivative, times the actual change. Whether you use dx or delta x, it doesn't matter. So here, whether you call that dx or delta x, it's the same distance. That's not changing, but the y will be different. So approximate error in f is really df, that's this derivative. Approximate error in y is dy, and the percentage error of f is df divided by the original times 100. That gives you the percentage. So first example, we're going to kind of find what differentials are. Take dy dx, that is 3x squared plus 3, and dy, if you cross multiply, is 3x squared plus 3 times dx. That's differentials. That gives you a very good idea of what delta y is. We're going to do an example and find the exact difference between those. Same deal here. If I want dy dx, that is 1 over twice the square root of x squared minus 4 times negative 2x. And if I want to find dy, that would be negative x over square root of x squared minus 4 times dx. Fairly simple. And I'm going to give you an example and show you in comparison what you're finding. Here's my next example. We want to find the exact change versus the approximate change. So if I put 3 in, I get 1 over 3. If I move a delta x, now I'm really looking at 3.1 and 1 over 3.1. So the actual change in y would be 1 over 3.1 minus 1 over 3. The actual change, the exact change in y would be negative 3.01075. That's the exact change. If I find the approximate change, dy is negative 1 over x squared, dy dx. So dy is 1 over x squared dx. And the approximate change is 1 over the original, 3 squared is 9, times 0.1, and that would be, I plug that in my calculator and I get 0.111. And that continues on. Now when I plug this in my calculator, I made an error, I read the wrong number. That was negative 0.01075. So you see, it's accurate to 2 decimal places. if I look at the next problem, y equal x squared, if I want to find the exact change, if I start at 2 and I move a 0.1 to the right, so delta y is actually if x equal 2, y equal 4, and if x equals from 2 to add 0.1, 2.1, that would be 2.1 squared, 4.41. So the exact change in y would be y2 minus y1. The exact change in y would be 0.41 versus the approximate dy dx is 2x and dy is 2x dx. The approximate change in y is 2 times the original times the change. We call that error, by the way. And dy would be, that's a 4 times 1, 0.1 is 0.4, and you notice those are very close. So that's pretty much the idea. Gives you a very good idea of what the exact change is. Sometimes the exact change is a lot of work. Now, the sides of a square measure 8 meters with an error of 0.2 meters. Find the approximate error. Well, in the area is x squared, dA is 2x dx. So the approximate error is 2 times the original times the change, and that turns out to be 16 times 3.2 square meters. The percent error in this case is the change of a over a times 100. Change of a is 3.2. Area is x squared times 100. And if you plug that in a calculator, that gives you the error in your approximation will be roughly 5%. That's the percent error. And if I go for a sphere, for a sphere, the volume of a sphere is 4/3 pi r cubed. So the radius of a sphere is measured to be 3.4 centimeters with an error of 0.05 meters plus or minus. Find the approximate error. dV is, bring the power down, subtract 1 from the power, dr. dV is 4 pi, the radius is 3.4 squared, dr is plus or minus 0.05. So the change in the volume approximately is plus or minus 7.3 centimeters cubed. And the percent error is the change of V over the volume times 100. Well, the change in V is 7.3 plus or minus. Volume is 4/3 pi. The radius is 3.4 cubed times 100, and that turns out to be roughly 4.4%. So instead of finding the exact, that's what we have. And here's a problem. The power P in watts delivered to a resistor by P equal 10I squared. If I changes from 1.2 amps to 1.3 amps, determine the approximate change in P. Well, dP is, bring the power down, 20I times the change of I. So the change in the watts will be 20. I originally was 1.2. And when you go from 1.2 to 1.3, that's 0.1 change. And the change in P will be, let's see, 20 times 1.2. That's So that's 2.4 watts. And the percentage, oh, actually that's all you need. No percentage error here. If you want the percentage error, you know how to do that. That's 2.4 divided by 10 times 1.2 squared times 100, if you wanted to. But they're not asking for that. And this is how it's normally used. This is an actual application where this is applied. Use differentials to estimate the amount of paint needed to apply a coat of 0.2 meters thick to a hemisphere dome. So hemispheres look like this. Where you have a diameter of 100, so R equal 50. And what you're going to do, you're going to add a 0.2. It's thinner than that, of course. Coat of paint. So they're asking how much paint would you need? Well, we know volume of a sphere is 4/3 pi r cubed, except this is a hemisphere, that's half of it. So volume is 2/3 pi r cubed. dV is actually 2 pi r squared dr. So the amount of volume, the change in volume is going to be 2 pi. The actual radius is 50. The change is 0.02. So the change of volume in that would be roughly 314.15 meter cubed. Now, just to demonstrate the exact amount of paint that you need to buy, the actual change in V is 2/3, because it's a hemisphere, 2/3 pi times the volume cubed, well, times r cubed, so this is 50. If you add a 0.2 to it, isn't the whole thing 50.02 cubed minus the original, which is 2/3 pi times 50 cubed. That's the exact amount of paint that you need. And if I plug this into my calculator, if I factor 2/3 pi out, and I plug that in my calculator, I'll get 314.28 meters cubed. So as you see, this is a very good approximation compared to the exact. We're off by simply 0.13 meters cubed of paint, which is nothing compared to 314. And that's really how this is used. Percent error. The sides of a square